This is just a little simulation just to try to help you understand the photoelectric effect a bit more clearly if you've found it a bit difficult. So like we had in the previous one, here's our plate. So here's a zinc plate. Over here you can choose your different metal. So just put it on a zinc plate because that's what we used. There's electrons on here. Can we knock these electrons off? Well, here's our little dim green light. Okay, no electrons are coming off. You'll notice there's no current in the circuit. What do I do to try to knock them off? Well, one thing I could try to do is to make the light more intense, so I could go up and get a brighter and brighter light. But what you'll notice is still nothing happens, okay, so there's no electrons coming off. Okay, if I turn that into a photon model, what that's telling me is that none of these photons have got enough energy to knock off one electron. You have to have one electron knocked off by one photon, and none of the photons have enough energy. Okay, so if I turn the intensity back down again, what I could do is I could change the wavelength of the light. So if I go from 500 nanometers up through 400, 300, okay, somewhere up here eventually when I get past the threshold frequency, I get to the stage where the electrons start getting knocked off. I start to get a current flowing down through this tube. Okay, notice the electrons come off with a different range of energies, okay, because some of them are right on the surface, so they get the entire energy of the photon, so you get the work function to knock the electron off, and then the rest of the energy is all kinetic energy. Some of them need some energy to get them to the surface and then get knocked off, so these ones that are coming slower, these were buried a little bit deeper into the metal. What difference would it make if I increase the intensity? Well, think about what you're going to see here. More intensity means there's more photons. More photons per second means more electrons per second, and more electrons per second means more current. Okay, if I change the metal, so if I go from zinc here to platinum, okay, let me just go back a bit. What you'll notice is that at this wavelength, platinum doesn't lose the electrons. If I go back to zinc, the zinc does lose the electrons. The platinum doesn't lose the electrons. What does this tell us? Well, it tells us that the work function for platinum must be higher than the work function for zinc. We could do the maths here and work out 220 nanometers relates to a certain frequency, which relates to a certain energy, and that energy must be more than the work function of zinc, but less than the work function of platinum. Okay. The other thing you can do with this animation is if the electrons are coming off, you can use this battery to work out how hard it is to stop them. So if I make a negative voltage over there, you'll notice that the electrons are just about still making it across. The most energetic electrons, if I just turn this far enough, the current drops to zero because even the electrons with the most energy don't quite make it across the gap. This gives us a stopping voltage. They call it 4 volts, which means that the most energetic electrons must have 4 electron volts. Okay, so you could do a calculation here where you do 120 nanometers, turn that into a frequency, turn that into an energy, turn that into electron volts, and you'd know that the work function was 4 electron volts less than that energy because the most energetic electrons have still got 4 electron volts of energy left. Okay, I'd really recommend that you Google PHET, the Colorado University website. This is a free animation. Lots of really good stuff on there which you can have a little play with to give you a chance to get used to these kind of animations.